Our last speaker today is Peter Diener. Peter is a professor of physics at Louisiana State University. He is also a maintainer of the Einstein Toolkit, and his research interests range from loop quantum cosmology to self-force and neutron star mergers. He will be talking about TOV example today. Thank you, Peter. You can continue.
Okay, yeah. So now we are going back to where we left off in the cactus tutorial. Hang on, let me. Can I minimize that so I can see my scroll bar here? So we just if you finished running the Hello World program, then the next step is to try to run a simple, very small example of some real physics, but not at a resolution where you can actually trust anything. So this is just running a single TOV star that will just oscillate a little bit once we get it going. And for that, of course, we need a parameter file. Oh, and Behan, can you keep an eye in chat in case there's any questions, because I can't do that while I'm doing this.
I will be monitoring the chat for the questions.
Okay. And so in the first step is to go to this cell here, where essentially what we just have a complete parameter file that we're just going to write into a file. I will quickly do it, and then we can go back and talk about a little bit about what is in the parameter file. But first, I just want to get it going so that we can get the run started, because they take a little while to run. You can see it says overwriting because I'd already had it done. That's why that is there. So now we go to into the cactus directory, and then we execute this command here, which is just a little bit different from what Steve showed you before, where there was a create run command to SimFactory. Here we will start by just creating the simulation. So that will actually not launch the job, but that will be done in a different step. And so we just make sure to remove if there was an existing one, and then we just call SimFactory with the create command, and this is the name of the simulation we want. And we use the configuration sim and the PAR file we just created. And we get a little bit of output from that. Then the next step is to then start the job. And here again, we are executing bash command. We make sure we are in the cactus directory. And then we say, instead of doing as before the create run or just create, now do submit. So we will say, okay, submit this simulation. We want to use 2 cores and 1 thread per core, so 2 totals, 2 total. And so let me just get that going. And we can now see that the submit was done successfully, and I have a job ID of in Slurm job ID of 80. Let's see where. Okay. So now, we can actually then check with another SimFactory command called list simulations what the status is of this simulation. And when I do that, you can see the output is that TOV-ET is active and running, and has the job ID 80 as I expected. And then also, in this case, with the way that things are set up here, the output of the simulation is redirected to a file somewhere that is controlled by SimFactory. And so in order to see what the output is, we have to do this SimFactory bin sim show output, and we use the -- follow to see whenever things is updated. And so if I click on execute that cell, you can see that the job has started. And if I scroll down here, you can see that we have actually started to get some output from the simulation. So let's go back up here and just take a look at the parameter file and go through and see what has all been set up here. So in the beginning, we have these active thorns entries, which essentially just activates the different thorns that are needed for the simulation, like this time, and the mol is the method of lines time integrator. We need our basic coordinates, so we use chord base and card grid 3D. We use the boundary thorn, and I don't actually think that static conformance should really be necessary. It's probably just a leftover. And then we use various base thorns like symmetry stuff. We are using some symmetry stuff. ADM base that sets up the ADM variables for the space-time evolution. TMU base that have information about the stress energy tensor, and provides and hydro base that provides the grid functions that contains sort of basic hydro quantities like density, pressure, and stuff like that.
Peter, there's a screenshot in the chat. It says thorns not found. Probably it wasn't built, and I don't know how we
hang on
submitted it.
If somebody, I hate to tell you this, but if somebody got that particular thing, what I would tell you to do is rerun that untar command at the top. Yeah. Because something went wrong for you. I can't tell you what, but if you rerun that untar command and you can skip all the subsequent build commands, then you should be able to get this to run without that error.
Thank you, Steve.
Thanks, Steve. And then we have, so this is not using Carpet X like Steve's last example, but this is just using the previous version of Carpet. So we have a bunch of things related to that. So let's go and take a look at some of the parameters here. As Steve just mentioned, we have different termination criteria. Here we say, okay, we want to use the evolution, the computational evolution time for our stopping criteria, and we say, okay, we want to run until t equals 400. There's some information here about how to convert that to actual physical time. But so let's go. Termination trigger is not interesting for the physics part. So we have to set up a grid. And in this case, we set up a grid with minimum value of 0, starting at the origin, for both X, Y, and Z, and then just a box that goes out to X, Y, and Z equals 24. And we do this with a pretty coarse resolution. So essentially, we just have 12 cells on this coarse grid here. And then we use carpet grid 2 to set up another refinement level. So we can see that we set up as a center that is centered at the origin with radius 11, and so essentially we set up a finer grid inside of the coarse grid here that goes from 0 to 11 with a resolution of 1. As I said, we are setting up the grid to only go from the origin and to in the positive direction. So we're setting up an octant here, and so we have to make sure that we have some symmetry cells on the for the negative x, y, and z coordinates, where for things to work out in this case, we have to make them 3 cells wide. And the shift outs are some that essentially means that with the ones here that then it works with a symmetry boundary, and the upper boundary is a physical boundary. So there we don't need a shift out. And then we also make sure to tell a thorn called reflection symmetry that it has to reflect the data across the x-axis or the y-axis and z-axis. And since we have a grid point at the origin, we set the avoid origin to no. As we are dealing with matter here, we have to set up have storage for the stress energy tensor that is needed to interact between the space-time evolution thorn and the hydrothorn. And so we specified that we need storage for the stress energy tensor. Hydrobase, we specify, okay, we need 3 time levels. That all depends on what time integrator you're using. In this case, it's enough with using 3. Then there's some carpet parameters here. So when we set up initial data, we only fill the actual state vector with the initial data, and this tells carpet that it should just use the remaining storage bins or storage or time levels for as scratch time levels for the time integrator. We allow for 10 refinement levels, even though we only use 2. And we specify that the go size is 3. And that should be, of course, consistent with your numerical scheme. And then we set up that when we prolongate from the coarse to the fine grid, that we using third order interpolation in space and second order interpolation in time, since we're using subcycling in time here. We are setting the Courant factor to be 0.25, so that means the time step will be a quarter of the finest grid resolution on the fine grid. And
Peter, there is a question in the chat. Alessandro asks, can you explain more about the time levels?
Oh yeah, so when we do a time integration, we have to use some time integrator. And many of those need some intermediate storage. For example, so here we're using RK4. So RK4 has 4 intermediate steps. And so we need some scratch storage for storing the data on intermediate steps before we can get to a full time step again.
Peter, you might want to say a few words about what prolongation is. I don't think the students know that.
Okay, yeah. So prolongation is when you're using mesh refinement, and in this case, we are doing what I call subcycling time, meaning we take that means that we first take a full step on the course grid. Here we only have 2 time levels, and then we take 2 steps on the fine grid. So we go from the beginning to half the course grid step, and then we take another time step to go to the full course grid time step. And in the process, of course, when at the boundaries of the finest grid, we have go zones, and of course those have to be filled with data from the courses grid, and that is called prolongation. And so essentially it's done by interpolating data in time between where we start and the first time step. We interpolate in time in order to get to the intermediate fine time step, and then we also interpolate in space from the data on the course grid. And of course, this has to. So in RK4 we have 4 time steps per full time step on the fine grid, and for each of those sub steps we have to get data from the course grid in order to be able to take finite differencing in the interior of the finest grid.
Thank you, Peter. I think we can move on.
Okay. So in this case, we're using what is called a low storage RK4 method, where it's built so that you only need one scratch level to evolve things. Let's see, we have NaN checker activated, and we check every so often for NaNs in the simulation. And this is the list of variables that we check NaNs for. So essentially all the physical variables, the metric, lapse, shift, and density, internal energy, pressure, and velocity. Okay. So the hydro evolution is done using a thorn called GR Hydro, which is an old workhorse that has been available for a long time. That has some parameters specifying stuff like what Riemann solver to use for the reconstruction of data in the method, and here we're using a simple polytropic equation of states, and those are selected with these parameters here. And the reconstruction method is ppm. So I don't have time to go into all the details about the hydro methods. I hope there will, or either has been or will be some overall overview talks on different hydro methods.
Peter, there are 2 questions in the chat. First is, when do I need to create a new thorn to tackle a problem?
Well, that's a good question. Well, I guess it depends on. I mean, typically when you do research, you want to do some things that nobody has done before, and that often means that you need to actually create something new that works, that actually does what you have. But it is possible that that everything you need is already available in the Einstein Toolkit, in which case you can just select the different thorns that provides the methods that you have or that you need. So I don't think there's a simple answer to say when you have to write your own thorns. It all depends on what you want to do and what has already been done in the code. And it also might be that you can just make a simple modification to one of the existing thorns to provide the functionality that you need.
Thank you, Peter. There is another question. What is the purpose of using a mask in this case?
A mask. Let's see, where's the mask? But I don't. Can they specify where they saw the mask? I don't. Oh, space mask, use mask. Actually, I have no idea what that is. Why that is there.
I think this is just required for the GR Hydro. When you activate GR Hydro, it requires this to be turned
Okay.
on, yes. But I might be wrong, yeah.
I mean, there's no risk for in this case of collapse to a black hole. So I don't really understand why the mask should be necessary. But as Steve also said before, normally you don't actually start from scratch when writing a parameter file, and so something like that probably came from a previous parameter file that was the basis for this one. Let's
Thank
see.
you.
Let's see. Okay, so okay, it looks like we are not providing any boundary conditions for the hydro because the hydro is all in the interior. And okay, so then we go on to the spacetime evolution, and that is done using MLBSSN or McLachlan, as we call it, and that provides the evolution for both the metric and the lapse and the shift as well as the time derivatives of those. And we need 3 time levels for the BSSN variables, and then we have parameters to specify the that we're using 1+ log gauge. So we have this harmonic n and harmonic f parameter specifies that a specific type of the lapse evolution that has proven to be very useful for many things. And then there's a warning here that is slightly misphrased. These are not selecting geodesic slicing. We are still using 1+ log slicing, but they turn off the gamma driver shift, so that if you actually had something collapsing to a black hole, you would run into problems that you get with the lapse collapsing, that you get slice stretching, and then the run eventually will die. So if you want to actually have something where you collapse something to a black hole, then you have to use better parameters for these quantities down here. We use a little bit of dissipation on the space-time variables, which is, I'm actually surprised that it's that low, but that's okay. And then the initial data is coming from a thorn called TOV solver. And we only initialize one of the time levels, and then we use the others as scratch levels, as I mentioned. And we use the initial data from for the metric from the TOV solution, the lapse and the shift as well. And we set the initial time derivatives to 0. And the pressure, density, internal energy, and so on, and velocities are all coming from the TOV solver as well. And here we then specify the parameters for the polytropic equation of state. We specify the central density in these geometric units, where the one solar mass is 1 and G and C is equal to 1. We use a fairly stiff equation of state, gamma equals 2, and a factor. So essentially this says that the pressure is 100 times the gamma to the second power. Well, the pressure is 100 times the density to the second power.
Peter, there is a question in the chat.
Mm-hmm.
Carpet does the centerings of the grid refinement levels by default in the origin of the domain. We can edit in the par file if we want it anywhere else, right? He asks.
Yes, yes. Up here, let's see. Oh, I went too far. Yes, you can. Let's see. Yes, I mean there are parameters to set to modify things, so you don't have the refinement at the origin.
And the second part, I wonder if the radius of the refinement levels is taken from the origin or from the multiple centers we declare.
Let's see. Okay, so the radius is from well, so we don't actually specify a center here. But there are parameters to specify the centers, but the default value is the origin, and then the radius will be the size of the box in each direction away from that central point.
Thank you, Peter.
Let's see where were we? We were here. Okay, and since the evolution thorn GR also needs to know about the equation of state that has been used to set up the initial data, we need to provide similar things here. I'm not really, so probably a technical reason why we have to both provide polygamma and GL gamma with consistent values, but I don't really know why that is. And then we say, okay, the out data has to go into the to a directory in the same name as a parameter file, and then here we specify what kind of I/O we want. And so the I/O basic is the I/O that comes on the screen into standard outputs. And here we want information about the physical time per hour and the maximum reduction of rho. So we essentially get information about what is the maximum density written to standard output. Every 512 finest grid iterations, but since we have 10 refinement levels maximum, but only uses 2, then this is probably every fine time step. We do some scalar output to files, where we get the infinity norm, one norm and two norm, and sums and maximum and minimum of various quantities, like the density and the pressure. And then we also get 1D output of the density every so often. And we are not getting any 2D HDF5 output. Oh, no, we are getting 2D HDF5 output every 2048 finest iterations of just the density. So let's take a look here at how the simulation is going. Okay. So because there are probably other people running, we had only asked for a certain number, a certain amount of minutes. And so it didn't quite get to t equals 400 before it got killed by the queuing system. But that's okay. We can still do stuff, I think. And so this is the iteration number. You can see, because we have the maximum refinement levels at 10, everything gets counted in the possible finest time step on the finest grid. And so we only have output every 512 finest grid iterations here. And what you can see, this is the physical time. This is the time per hour that we requested. And this is the maximum density as a function of the maximum density available on the grid. So let's see. So in order to take a quick look at the data that we had generated, we can use something called Quibit. Quibit is very good at handling Cactus output. And if it's not installed, then it can be installed very easily by just doing a pip install in user space. And so let's just execute that. In my case, this has already been done, so you should all, and I think it should be the same for all of you, that it was already available. And Quibit has quite nice documentation available in this link here, and there's also a bunch of different examples that you can look at and figure out how to use it. And there are some quick scripts for plotting time series or plotting variables, and so we will try to use those right here. Let's see. So this is using the plot time series. We specify what is the where it can actually find the data, and in this case, it's in the simulations directory in TOV ET. This is the name we gave our simulation. We want to look at row, and we want to use look at just the output that Cactus generated, which contained the maximum of row as a function of time. And the final plot will be put into the same directory. And then there's another plot here where we try to plot row as a 2D plot. Again, data dear is home simulations TOV ET. the variable is rho. Here we specify plotting from 0 to 10, from the origin to 10 in X and Y. And the output directory again is there, and we want it in as a log scale. And in order to, because we have refinement, Quibbit has to interpolate data to the grid where we want, and we also want a color bar. So if we execute this, see, it takes a little while. Now that has returned here, and so in your simulation TOV ET directory, there should now be a row maximum and row X, Y, PNG files with the plots. And here's a little cell that goes and allows us to show this in the notebook here. So we specify the where the files are, and then specify the name for the first one. And if we look at that, you can see that we didn't get all the way to t equals 400 because we got killed because the server was busy. But you can see that the maximum density starts here, then it oscillates up and down, and it behaves as it should. And if we look at the density, you can see this essentially showing one octant, a quadrant in the XY plane of our TOV star. And you can see that we have pretty coarse resolution here. So the star goes to somewhere between 9 and 10, and we only have a resolution of 1. But this is, as I said, an example where you shouldn't trust the physics, but it just shows you some of essentially just a low enough resolution that that you can see that things are actually working. But one can also use Quibbit more generically and look at things in more detail. And for that, we have to import some stuff into the Jupyter Notebook so that we can look at things more detailed. And so when we execute this, it will give us access to the necessary Quibbit. And see where does this. Okay. So up here we specified the data there, the sort of the high level simulation directory that contains all the data. And the first step is simply to say, okay, tell Quibbit to take an inventory of what is in that directory. And so it will go in and look at all the files. And as you can see, so it says that there's no available scalar time series, no minimum time series, but there are 2 maximum time series of rho and density and pressure. Let's see, and then there's 1D data of rho of the density in X, Y, and Z, and then there's 2D data of density in XY plane, XZ plane, and YZ plane, and no 3D data. So when you want to use Quibbit, you have to sort of massage the data a little bit because of essentially of the refinement levels. And let's see. So here we essentially ask for all the XY or the XY data from the simulation directory for the density being placed into this data structure here. And we also asking for information about how many iterations have been done. And here there's I won't go into all the details here, but there's some Python code here defining some functions for plotting a surface that that uses some other functions to extract things, data from the different refinement levels, and get coordinate information that you can take a look at these and see if you can understand them later. And then it will generate using matplotlib will generate a plot showing that. And so if I execute that, you can see that essentially what it does, it plots the density on the two different refinement levels with different color maps. So on the coarse grid, we're using the blue color map. On the finer grid, it's using the red color map. And so you can see that there's this region here going from 0 to 11 has higher resolution than the coarsest grid. And let's see, the next step was simply to let's see. What is it we're doing here? Making a plot of the pressure. Okay, so it reads in the pressure from the time series data, the maximum pressure from the time series data. And let's see. Oh, and then it reads in the density and the pressure from the data, and then it calculates what pressure you would get using the equation of state giving that density, and then it makes a plot of those two on top of each other, and writes out an information about what the maximum difference was. And essentially this plot simply shows that the equation of state was used correctly by the evolution thorn and that the pressure and density are always consistent with that equation of state. Let's see. And then there's an example here where we plot with an equatorial slice of the rest mass density at the initial separation or initial iteration. And so let's see, it gets the density at the last iteration, or no, at iteration number is the first iteration, and it takes the mesh refinement data and interpolates it to a uniform grid that goes from 0 to 10 in each direction. and then it undoes the reflection symmetry. And so if we do this, we should get a plot that shows the whole star. And again, you can see very coarse resolution. And this final cell here, whoever has made this, I don't actually know who made this, has encoded a time series data into a string that gets extracted and then plotted together with the density that we actually calculated in our simulation. And if I execute that, you can see that the reference data contain data from the full a full t equals 400 simulation, whereas ours stopped at about 90. But you can see that as good agreement. You might wonder why doesn't it agree completely, and that's because the reference data was downsampled so that it only showed every 10th time step compared to what we have. So the simulation, even though that seems to be a little bit of offset here, essentially is just because the blue data was downsampled in time. And here's the function that they use to the Python function or piece of code that they use to take the full t equals up to t equals 400 simulation and encode it into a string, the string that you see up here. And I guess that's the end of it. So if there are any questions, then yeah, now would be a good time. And of course, if you didn't get through, you might want to try to run the simulation when the server is not so busy, so you can get the full data. And if you didn't manage to get things run now, again, you can do it at your leisure later.
Thank you very much, Peter, for a very nice and informative tutorial. Now I will stop recording.